Hello, everyone. Very excited to be here. Thank you for having me and for hosting us so well at this conference. Today, I want to talk about healthy artificial intelligence at any scale. There's a lot I'm going to unpack today, so be ready. If you want to take notes, take your notes out. Before I start, a little bit about me. I was born and brought up in India, but I'm currently based out of San Francisco in California. I am a machine learning solutions architect at Nvidia, where I work with Nvidia's largest customers on understanding their training, inference workloads, their AI infrastructure, and actually working with them to improve it. Throughout the past 7-ish years, I have published research papers on different fields in artificial intelligence, starting with classical machine learning, deep learning, natural language processing before ChatGPT became a thing, then going and doing research at Stanford on AI and cognitive neuroscience, and working with different industrial projects at Google, other places as well, on large language models, on training and inference. My goal in the next hour would be to distill these years of experience and learnings with you on how to design healthy machine learning, healthy AI pipelines and workloads. Okay, I'll start with talking about what, why, and who of healthy AI. Then I'll talk about different
spectrums of the scale spectrum, starting with the small scale AI workloads, medium scale, and then going over to large scale AI workloads, and how you should be looking at each of these workloads and how you can actually optimize and make different workloads more efficient. Then I'll talk about the common pitfalls where I usually see people digging their own graves and stumbling and falling into them, and how to avoid it. Finally, I'll wrap up with some key takeaways, and we'll have a fun question and answer session. Before I go into what is healthy machine learning, I want to talk about why you want to do healthy machine learning. So can you give me a quick raise of hands if you have ever either trained an AI model or tried to host an AI model? Okay, quite a good number of people. Now keep your hands raised, or raise again, if you have ever blown money on, or nights on compute on doing either of these tasks, and would want to reduce the amount of time you spent or the time it took for you to actually get your workload up and running. Okay, so you're going to have a fun time today. Now, healthy machine learning, what does that mean? It means AI models that are not just correct, but are also efficient, scalable, and robust. How I like to measure them is usually like these 6 vitals, which is first, latency, which means how much time does it take for your request to complete. Second is throughput, which is how many concurrent requests are you able to process in parallel in your system. For inference, that means that, but for training, that can mean how many data samples are you able to process at the same time in your current setup. Third is utilization. Given the compute that you have available, how are you able to utilize it, and how much are you able to catapult on it, and how much of it is actually sitting ideal? Fourth is cost. Naturally, it's an important vital about how much money in terms of GPU hours, dollars, or even your own personal time are you spending on getting that workload up and running and to its completion. Finally, fifth is carbon footprint. Any workload that you run, it runs on some compute that consumes electricity and naturally contributes to the overall carbon footprint of this planet. And finally, not the least, is correctness, which means how well is your model or workload doing the task it is supposed to do. Not just how accurate it is, but how well is it doing what it is supposed to do. In this talk, I will try to share practical techniques to optimize both training phase, which is developing your own model, and also inference phase, which is when you host your model for external people to query from, of machine learning projects across different scales, and these are the vitals that we'll try to balance off. Knowing these vitals is important because you should know what are the metrics that you care about before going into a project and have tangible ways of measuring these vitals as you induce optimizations throughout. Now, whose responsibility is this healthy AI? I believe health is a team sport. Whether you are collecting data, whether you're helping load that data, whether you're helping training the model, whether you're helping host that model, or you're a site reliability engineer, I believe everybody owns your workload health. Okay, going on to the scale spectrum, I like to think of it as three broader scales. The first being small scale machine learning. What does that mean? That either you are a single user or you are doing a research project in a research lab, or you'd want to do something which is a quick prototype or a quick iteration proof of concept situation. Usually you are either doing it on your laptop or like a small lab server that you have. You're usually using somewhere between thousands to like less than a few million data samples to train your model. And your main focus here is rapid development. In medium scale, things start scaling up. You are in a team situation where you are either using a heavy server or you are now switching to GPUs, where you can use anywhere like between 1 to 8 GPUs or a node or maybe a few nodes. Your data scale is also increasing. You're now in like few millions of samples to less than like a few billion samples of data that you're training on. And your focus here now shifts to, instead of using one sample in the entire pipeline, how can I increase my throughput, which is how can I increase the number of samples that my model can process at once. Finally, large scale, this is more enterprise or cloud heavy, where you are now operating on more than a few nodes. It can go onto a cluster, a data center, as big as you can think of. And your data is also scaling up usually. It's like few billions, maybe more number of samples as well. And here, naturally, your focus shifts to how can I do large-scale computing? How can I have, you start looking at distributed computing or disaggregated inferencing, something that I will try to disambiguate in today's talk as well. The key point to note here is that as your scale increases, your bottlenecks will also shift. And hence, different optimization techniques will work depending on which scale you're operating at. Let's start with small scale AI, where you are looking at a local or a prototype situation and you're trying to optimize for agility, which means that you want to design something quick, get quick feedback, and see if your pipeline that you're designing even works. How you can ensure that is some suggestions that I want to talk about today. First, using efficient libraries. I think Robert kind of already touched on it, that instead of using simple Python, there are very advanced libraries like NumPy, if you're doing scientific computing, Pandas, if you're doing, you're working with data, scikit-learn for data analysis, for data visualization, you have matplotlib, and all of these libraries are built with a very specific goal. So using these libraries to do your workloads already helps you as opposed to just using simple Python, and we'll see that in the next few slides as well, how. Second is profiling. Profiling means understanding what are the bottlenecks in your code, like which part of your code consumes the most time. And as your scale will grow, I've worked with people, and I've done this myself, where profiling plays a very big chunk whenever you see your system is slow. And also we'll see today how to profile your system. Third is, and I believe is the most important, is keeping things lightweight. It is something that took me years to learn. Whenever I would be handed a new research project, I will collect the data, and I will look at whatever model I thought would be best for it, and I would just go on to train things. I would just jump into it because I wanted to get results quick. And it took me a lot of time to realize that that's not the best practice. The best practice is, instead of using your entire million sample data set, you use a subset of data set, you use a smart model, and you see if the pipeline, the hypothesis you have even makes sense. If it does not, then how can you make it make sense? And only when something works on a smaller scale, then scale it up. It's very frustrating to spend
3 nights training a model with so many high hopes, only to find that something very basic was really wrong, like your entire model hypothesis was wrong. So keep it lightweight. Use as simple a model as you can. Use a small subset of the data set that you have, and make sure that that works, and then start increasing your data. Then start making the model a larger model than you are using. Fourth is algorithmic efficiency. Here I believe it's better to use a small, basically you should be emphasizing on using good data structures and good models by truly understanding what your use case is. Instead of trying to have a classification model or a classification inferencing task on a next token prediction model, it makes sense to understand what your use case is and use an algorithm and a data structure that makes sense for your use case. Final is planning for edge inference. This also involves around understanding what your end application is going to be. If your end application is something that you see being deployed on a mobile system or on a small chip in a remote situation or an on-prem customer base, then plan for it. Use like a simple model or use models that can be distilled or compressed into a smaller environment to make sure that you design things by considering those. Now let's see some of these things in action. First, I want to talk about vectorization, and I will have some code pieces as well here. To demonstrate how vectorization is important and what vectorization is, we will try a very basic task. I have an array of numbers, and I will try to square each element in this array. First, I use a loop operation. So here, if you can see, I'm going over each number in my array, and I'm squaring it independently, sequentially. This is a simple loop operation. The second method I do is I convert this number into a NumPy array, and I'm going to do this feature that NumPy gives you, which is you can just do a square operation on the entire array at once. And what this means essentially is NumPy is optimized for scientific computing. So NumPy inherently inside has optimizations that can parallelize this squaring operations, since all of these operations are independent. My second square does not depend on my first square at all. So NumPy will go ahead and square these by launching multiple threads, and that is how it makes it efficient. Let's time things, and we see that the NumPy vectorize operation is 56 times faster than just looping sequentially. This can feel small, but in a real-life situation where you're trying to train artificial neural networks or AI models, you will have billions of matrix calculations. And if you start iterating over each of them, you will quickly start seeing how these costs add up. Second that we will see here is profiling. We'll try to find now in this code that we saw before, slow functions. Without, sometimes you don't want to probably add time functions throughout your code. So without adding that, how can we know which functions in my code are acting slow? So here, in the previous code, I essentially just added both of the methods that we use as separate functions so that we can see clearly. Various tools provide profiling services, by the way. Here, I'm using cProfile by Python. But if you're using, for example, if you're using Nvidia GPUs, Nvidia also has Insight systems, which can give you a kernel-level detailed profiling information as well. Now, I've used my profiler, I've enabled it before launching my main code, and I disable it as soon as I'm done with it. I also sort my stats by a cumulative value to see, to sort them by the time taken. And this is my result. I see, as you can see here, the slow Python loop square is taking up 300 milliseconds. You see how many calls are made, you see how much time it takes per call, and this actually helps you understand where the bottlenecks in your code lie. So, because I believe you can't optimize without awareness. So profiling actually helps you be aware of where things are getting slow and how, and then you can look into how you can optimize it. Now that we understand how to ideally do things at a smaller scale, let's start scaling things up. Let's look at medium scale AI. Here you're scaling up from like a simple laptop or maybe a single CPU to maybe a GPU as well. And your goals start shifting to optimizing for throughput, which is how many requests you can process in parallel, either in training or in inference. The optimizations that you would want to consider for this kind of a scale is first, leveraging accelerators. If you start seeing that your training time is taking too long on a CPU, then looking at GPU, looking at other accelerated training frameworks like PyTorch, like TensorFlow, like JAX. I will show the accelerator part as well in the next few slides. Secondly, like efficient data pipelines. So there's different ways of loading your data when you're training your models. You could either use pandas.readcsv, and try to load your entire, like, 300 million data samples at once and spend the entire 4 hours hoping that your timeout doesn't get triggered. Or you could use something more advanced like PyTorch, so PyTorch has data loader class available that you could use, which inside it inherently will load your data very smartly in batches, and it also has an asynchronous mode, so you could load your data in parallel, like in the background, while your main function continues doing other tasks of setting things up, which I think is really smart. Another optimization technique is tuning batch sizes and parallelism. So here, actually, I wanted to spend some time talking about batch size. What this means is, instead of sequentially doing one data sample at a time, now I'm going to send a number of, like, accumulation of samples together at once, either to my training AI model or to my inference requests. For inference requests, we have inference engines that already exist, and I will talk about them in a minute. But in training, for example, it's worthwhile spending some time, try to experiment with what is the ideal batch size for your training model. What that means is, if I have, instead of sending one data sample at a time in my iteration, if I send, let's say, 32 samples at once, now my X vector, instead of becoming my input, instead of becoming a single value, now becomes a vector. Similarly, my weight matrix, instead of the original vector, now it becomes a matrix, because I'm trying to calculate the weights of all of these inputs at once. And similarly, my bias variable also becomes a vector. Now I do my x into w plus b operation, and because we already saw how vectorization improves things by doing multi-threading, this entire forward pass, instead of having 32 forward passes, gets reduced into one operation, one extremely optimized vector operation. Similarly, for loss calculation, for loss back propagation, all of this becomes really optimized when you start increasing your batch size. It's worth knowing that batch sizes, you can't just go from like 0 to, like, let's say, 1 million batch size, because you are limited by how many things you can fit in your compute. So it's worthwhile doing an experiment in the beginning when you're training your model at a medium scale to find what is the optimal batch size for your setup, for your data, for your model, for your compute. What is the max batch size that you can have without compromising with the vitals that we discussed before, without compromising with the throughput? Because what you will see is that as you increase the batch size, your throughput, that is the number of samples you can process at once, will go up only to a certain point, after which you will see a knee-jerk reaction in your compute or your latency. Latency is how much time it takes for the iteration to complete. And this point, after which you see your latency spike up, is the point which is the max batch size that your current system and your current setup can handle. Use that when you do your training, and you will see your training becomes exponentially faster, and your GPU utilization or your compute utilization also is extremely high.
Finally is the inference engines. So to do the same thing for inference, there already exists inference engines like TRT LLM, VLLM, SGLang, etc., which have inbuilt infrastructure tools for you to leverage without having to write this entire pipeline from scratch yourself. So they will have features like KV cache, which we'll talk about as well today. They will have features like batch sizing and making inference really fast on multiple instances of the model. Let's see some of the accelerators in action. The setup, for the first thing I want to show is how things accelerate when you switch from CPU to a GPU. The setup for this is I have like a very simple 3-layered neural network. I have a batch size of 64, and I initialize my input and output data randomly to be 64 samples and 1,000 features. Now, for a CPU workload, simply I will calculate my output by sending my input through the model. I will calculate the loss, I will backpropagate my loss, and now I will calculate how much time it takes. And I saw it takes 22 milliseconds for this very simple workload to finish up. If I were to switch to GPU, that would mean that I'm going to offload my model to the GPU, my optimizer as well, and my input and output. But here, I'm going to do my output calculation, my loss calculation, and my loss propagation all on the GPU. GPU is something that is optimized to do parallel tensor operations. And all of this operation of calculating the output in a vectorized way, of calculating the loss between two vectors, and backpropagating this loss are all mathematical tensor operations, which GPU is basically existing for. So offloading all of this to the GPU gives me a 14x improvement. This 14x can look like a small number, but trust me, in real life situations, it really is not. And this is given such a small scale. And as this scale will go up, you will see that this improvement also goes up. And I also will preface by saying I used a T4 GPU, which is like seven generations or 7 years old. So if that gives me a 14x improvement, I don't even know what Blackwell or H100 will give me right now. The next accelerator I want to talk about is PyTorch. PyTorch or a similar training accelerating library like either JAX, TensorFlow, or something else. I'm using PyTorch for reference because that's what I see a lot of people use right now. The setup is, again, very similar. I initialize my input, I initialize my output, I initialize my weights. Here, first, I will use NumPy, which is very simple and honestly, which is what I used when I was beginning to learn machine learning in first year of undergrad. Here, I will calculate my output by multiplying by doing a dot product of my input with my weight vector and adding bias to it, smoothing it using sigmoid. I calculate my error and the differentials of my weights and biases that need to be updated, and I actually go on and update these vectors. I see it takes me 120 milliseconds to do this. Now, if I were to use something like PyTorch, how will this look like? I'm going to offload, not offload, but I'm going to create torch tensors for my input and output. I'm going to initialize using torch neural network class. And I will initialize my optimizer and my loss function from PyTorch itself. So PyTorch is an accelerated machine learning library that consists of hundreds of classes that machine learning practitioners need and use in daily life. So instead of having to write your own sigmoid function, your own smoothing function, your own loss calculation functions, it provides you one line of code functions which internally are heavily optimized for how the calculations happen. So now my training code, as you see, also becomes really simple and very intuitive, where I can simply send my inputs through the model and calculate my output, and similarly calculate my loss and also propagate it all in each one line of code. And it gives me 3x improvement. Again, this PyTorch code I wrote on CPU. So this is CPU, this is not even GPU, and it's already giving me a 3x improvement over such a small data.
Okay, I hope you're still with me because now things are getting a little crazy now we're scaling up to a large scale AI model. This is a more enterprise or a cloud situation where your data and your model size is going into billions. What really starts mattering here is distributed training and how you set up your distributed training infrastructure. This will include sharding your model, sharding your data, sharding your tensors. We will talk about it in the next few slides. But this also includes reducing your communication overhead. What does that mean? So now that your scale of model is so large or your data size is so large that it potentially cannot fit on a single GPU or it does not make sense for it to be on the same GPU, you start distributing your training or you start distributing your inference across multiple GPUs or across multiple nodes. When you do that, your GPUs need to talk to each other. Your compute instances need to know what the others are up to and if there's something wrong going on. And this is where communication starts playing a big role. We'll also see once I explain in the next slides how sharding works, of how many communications actually happen. And the more number of communications happen, the more important it becomes what your communication protocol is. Having an outdated protocol or having a really slow protocol, I have seen firsthand can either slow your entire training process down, can slow your inference down. It can lead to like your data packets being lost as they're trying to communicate with each other and becomes really important. That does not mean that you need to go in a data center and physically change the wires that you use, but it's good to be aware of what your communication protocol is for the system that you're using. Something like NVLink or InfiniBand is more latest, and I've usually seen that being more performant in terms of communication. Fourth thing is auto-scaling. So when things start scaling up to that enterprise level scale, you can't simply send your job to train on a GPU, allocate it yourself. You need something more sophisticated that can auto-scale either your training instances or your inference instances based on what workload you have. There are tools like Kubernetes or in cloud services, we have functions. For example, in Azure, you have Azure functions, which will auto-scale the instances that you have launched on your compute. For example, if you have deployed your model through Azure functions and your users go from 3 to 3,000 at a particular point, then Azure functions will go on and automatically deploy more instances of that same model on your compute, hence making sure you're using more compute only when you have the need for it, only when you have the number of users for it, and you don't have to manually sit in and deploy yourself. If you've seen Silicon Valley and if you've seen I forgot the name of the character, but like he goes in through the garage and like physically gets the wires out. Like Kubernetes or Azure functions will make sure that you don't have to do that, ideally. Even though we did have to do that in my last startup when things weren't scaling beyond control. Finally, high-scale inference, which means as your inference requests are growing larger, you want to make sure you can reuse as many pieces as you can get instead of recomputing them, because compute starts becoming your bottleneck there. I think I will have enough time to talk about one of the methods, which is KV cache, but there exists other methods in addition to that as well, like speculative decoding or disaggregated inferencing as well. Now let's start seeing some of these things. Let's talk about parallelism. So there are different kinds of parallelism that can exist that make a system a distributed system. I'll talk about 3 today, which is data parallelism, model parallelism, and tensor parallelism. What is data parallelism? Let's say I have like a small model. I have like a 4 billion parameter model, like a llama model. But the task that I'm fine-tuning it on, I have a billion samples for it. This is a lot of samples to fit on a single GPU on a training pipeline. Even if you can fit it, it can take a lot of time for the training to happen. And either I might not have the time or the patience for it, or I want to quickly iterate over it to see how good my results look like. In this case, I can opt for something like data parallelism.
What this does is that I can use, instead of one GPU, I can use 4 GPUs, and what I can do is I can send my model on all of these 4 GPUs, and for the large data I have, I can split this data into 4 pieces. And I can send data partition 1 to GPU 1, data partition 2 to GPU 2, and so on. And now when the training happens, I'm going to do a forward pass in parallel across all 4 of these GPUs, and once the iteration is complete, I will collect all of the outputs that I got, I will calculate the loss, I will backpropagate the loss, and I will redistribute the updated weights across these 4 GPUs, and my training will go on. Now this way, I've essentially distributed my training across these 4 GPUs by distributing my data and making the time that it takes to finish training really fast. So this is one way. Second way is model parallelism. This you would want to consider when your model size is too big, but your data size is in control. So let's say I want to train a 70 billion parameter model, which I don't recommend as the first model you train, but as things start scaling up, you might see yourself wanting to do that. Here, to train on a 70 billion parameter model, depending on which GPU or which compute resource you have, it might not fit on a single GPU, or even if it fits, the time it takes to train can become really, really high because it might not have enough RAM available for you to actually do the training really fast. So in this case, what you can do is you can split the model. So you can split your 70 billion parameter models into few billions of parameters, little models, and you can split them across different GPUs. And as before, each of your model partition will go on each GPU, and you will continue training. Once the iteration is complete, you will collect all the losses, you will calculate the error, you will backpropagate the new weights, and you will redistribute them and continue training, and it continues happening. As you can already see, this involves so many GPU communications, and hence the factor about communication becomes really important as well. Okay, more information, tensor parallelism. What this means is, tensor parallelism is a technique to fit a large model in different GPUs. It can exist in different forms, because as we were seeing before, all of the operations that I'm doing on GPUs is essentially tensor operations. Sometimes my tensor operations can scale up to be so high that they might not fit on a single resource. So here again, I start splitting them across different resources. This is one example of how tensor parallelism can look like, where you see that to get output 1, I just need to multiply my first row of input with my first column of weight vector. So I don't need the second or the third column of weight vector to calculate my first output value. What that means is that this is the opportunity to split things and do things in parallel, and that's what I'm going to do. And I split my weight vector into 3 objects, into 3 splits. I send them to different GPUs, ask them to calculate output independently, collect them, append them, and send it for the next steps. So this is what tensor parallelism means, splitting across tensors. Now let's look at KV cache. That was all about training. This is more on the inference side. KV cache, the need for KV cache came from attention and transformer models, if you've heard about them. In the next token prediction task, we see transformers being used a lot, and the essence of transformers lies in attention mechanism. What happens there is that you calculate the query keys and values for each token that you want to predict. So my query will be a matrix operation that will be calculated for my current token representation, but my keys and values are vector representations of all the tokens that have existed in the past and my current token. Now what happens, let's say I want to calculate the attention for my second token. There, I will be recalculating the keys and values for my first token and then for the second token. For my third token, I will be calculating the keys and values representations of my first token, my second token, and now the third token. As you can quickly start to see in your computer science brain, this is redundant information. What you do here is now you start caching things. Again, another computer science concept. So what that means is that when I'm calculating my second token representation, I am not going to recalculate my first token representation because it's not going to change now. So I'm going to cache that value as soon as I calculated the first time. And the second time I have to, the second token prediction that I'm doing, I'm going to reuse the result that I got from the first time. This is what the concept of KV cache is, and it ends up being phenomenally useful when you're doing a large-scale inference. It's, in fact, this is I think one of the reasons that VLLM, which is a very powerful inference engine, came into existence. Okay, common pitfalls so that you stop digging your own grave. The most common pitfall that I see is when people make things really complicated. And I will admit that I was one of the victims of this as well. It's very easy to use the largest model that you see, use the fanciest terms that you see. Now that you know what KV cache is, you want to use it for your use cases as well. But it's important to know, do you even need it? It's this is a question that I think is very fundamental to any research or any practical application as well, is do I need to use it? What is the simplest thing I can use to get to my goal? Is, after years of experience, is what I've learned. That instead of trying to have a really complex architecture that will take me 4 months or 5 months to build, and at the end of the day I find that it does not even apply to practical use cases, it is better to have something that is really simple, can perform well enough, and find if it works for my use case or not. So don't make things too complicated. Keep things as simple as you can. Know what you are doing and why you are doing it. Know the correct reasoning for your use cases. Know the correct reasoning for using the model that you're using. Know the reasoning for why do I want this data? What kind of data do I want? What kind of model do I want? What kind of metrics do I want to track? How do I want to track those metrics? Have good reasons for it. And this is something I learned from my time at Stanford, where I would talk to a lot of because I was doing psychology and neuroscience research. This is the contrast that I saw in good AI in neuroscience labs versus pure computer science AI metric chasing. Is psychologists or pure science people, they ask the real questions. Why am I doing what I'm doing? Why do I need to do what I'm planning to do? And what do I need to do to get to the goal that I have? Finally, this also relates with chasing metrics, where instead of simply chasing a benchmark, know what your end user cares about, even if you are your own end user. Understand what are the goals that you care about, and then compute what are the metrics that make sense for you. And oftentimes, surprisingly, you will find the general leaderboard metrics that you see are not useful to your use case at all. I also wanted to plug this paper that actually I think came out a month ago from Nvidia, which talks about small language models are the future of agentic AI, where it's a position paper which talks about how you don't even need a lot of times really large models, and smaller models 4 billion parameter models, 8 billion parameter models can also satisfy a lot of use cases in real life situations. So you might not need a 100K GPU cluster, or even if you need it, you would at least know why you want it, what you want it for. Okay, key takeaways from today. So we went through the 6 vitals today: latency, throughput, cost, utilization, carbon footprint, and correctness. So know what are the metrics that matter to you, and optimize with the purpose. I will caveat that by saying that at NVIDIA we have this concept of speed of light, which means know what is the North Star of the metric you're chasing, because you can't just keep going forever in that loop. So know what is the best you can get at, and then tangibly measure the progress you are making. One size doesn't fit all, which is the AI techniques that you have, they have to adapt to scale. Something that works for a smaller scale might not work for a larger scale. So just because somebody on Twitter is talking about a new technique does not mean that it must adapt to you. Know what the technique is for, and know what scale and use case you are working at, and see if it makes sense. Profile, profile, profile. And I cannot say this enough. Always measure the code you have written. How well will it do? What are the bottlenecks in it? And see if you want to or can optimize for it. And to do that, leverage this ecosystem. Instead of writing and reinventing the wheel from scratch all the time, which is something that I had a very strong urge to do every time, leverage the ecosystem that you have, which means leverage libraries like PyTorch, JAX, NumPy, Pandas, that so many brilliant engineers have devoted so much time to build. Use that work and accelerate yourself. Stand, or as you say, stand on the shoulder of the giants. And continual improvement, which means as your pipeline changes, as your workloads change, what matters to you will also change. So be flexible to change. Improve your workload with time. And ensure your machine learning systems stay healthy at every scale. I want to take a minute to help you put some of the things that we talked about today into action. First, I would like you to try it out, which means I want you to take one project, and this is me coming from a very academic setting and wanting to give everybody homework, is I want you to take a project that you're working on and profile it. You can use the C profile we talked about, you can use Nsight Systems, which Nvidia has, and I want you to identify one clear bottleneck, which can either be a slow function or it can be an underutilized GPU, and apply a relevant optimization from what you learned today. Even a small improvement is a win. Adopt a tool. Pick a new tool to integrate into your workflow from either the tools that you learned today or things that are adjacent to it. That can mean use something like Grafana maybe and integrate that into your workload to have like a Grafana dashboard where you can see how your workload is doing, what latencies it has, and how can you improve it. Finally, share and contribute. All the things that I share today, I learned it through either hard-learned experiences or through the community that we have. So discuss with your team or community what you learned today. Help other people know faster what they can do to improve their pipelines, their workflows. And contribute to open source projects or even forums by either raising PRs, improving documentation, sharing what you learned, and finding maybe even problems that you think can be optimized by some of the tools that you learned today. Yeah, let's make healthy AI a team sport. Thank you so much for your time.